Then, hello everybody, and thanks a lot for being here today, and thanks a lot for having me in general. Today, I will be talking about adapting to change, foundation model, APIs, and the past, present, and future of AI development. So the talks revolves around that during my years of work as an AI engineer, I witnessed a big shift in the way neural networks are used in real-world application, going from in-house training and in-house infrastructure to cloud infrastructure, and finally to fully managed ones with foundation model and foundation model as a service. The talk, the talk revolves precisely around this. It is a recollection grounding from where we started, where we currently stand, and where we're going. It's meant to be slightly speculative, and by nature of things, it cannot possibly cover the approaches that all companies have taken and will take, but it focuses more on small and medium-sized company or not AI native ones, and brings a fundamental call to action, encouraging the adoption of AI, as today the ecosystem really is mature and we can only expect more to come. With that said, let's dive deep. So the agenda for today, first of all, there's going to be a small introduction about myself and the company where I work, which is Kittle. This aims to give the context and the ground for the rest of the points that will be discussed in the next section, which are namely the past of AI, so basically exploring where we came from, the present of AI, so basically where we currently stand, the future of AI, where we're going, and finally, some concluding thoughts. If that sounds good, let's begin. So who am I? My name is Pietro. I am an AI engineer at Kittle, the most intuitive design platform. I have a bachelor's degree in computer science and a double master degree in artificial intelligence from the Technical University of Stockholm and Berlin. I've always focused and worked in the generative AI space, starting even before the Transformers era, when recurrent neural network and generative adversarial network were still the predominant architecture for generation. My career began in the research field, where I worked on creating a novel recurrent neural network architecture for concurrent generation of melody and lyrics, an approach that was never explored in the literature before. And then after around about a year, I decided that I wanted to be more hands-on, more on the engineering side of things. And I worked with startup in the generative AI space, building several systems, again, focusing on the engineering side of it, taking model and bringing them to production in a full MLOps lifecycle, from provisioning infrastructure for training to creating modular production-ready code, CI/CD pipeline, and finally monitoring models. For example, one of the projects that I'm mostly proud of is the most advanced AI lyric opera ever made to date, where with my team, we create a system for real-time generation of lyric singing voice using a combination of 4 different deep learning models for text generation, melody generation, then fitting the two together, and finally singing voice generation. That was pretty interesting. I'm now very happily working at Kittle. And before we dive on why AI plays such an important role in our company, it is important to give some context on what we do. We are one of the fast growing startups. We offer an intuitive vector-based editor that is used by tens of thousands of people every day. It offers advanced features like fully editable templates, advanced text editing, designer fonts, mockup, and actually much more. The goal since the inception of the company is to allow everybody, regardless of their proficiency level in graphic design, to create meaningful and impactful graphics. So as you can imagine, this is really a green field for generative AI, as it can greatly help the user to reach their goal even faster and more effectively. So for example, diffusion models, large language models, segmentation model, it's really all greatly applicable here. Just to give an example, all of this design that you see, we're creating using Kittle AI as part of the user workflow, whether it was to generate text, to generate images, to generate vectors, to vectorize images, to segment images, remove background, a lot of different creativity possibilities, as you can see. It's a pretty exciting time for exploring generative AI, for sure. So More on this, the AI tools that we currently build and serve are the AI background replacer, which is basically a segmentation and inpainting model, which is used to seamlessly create AI scenes for products. So it's possible to upload a picture of a product, then the product will be automatically recognized. There will be a segmentation happening to basically remove the background. And then it will be possible through inpainting to place it in different virtual scenes. Then we have the AI text-to-image generator, which is based on a latent diffusion model. We does then a prompt engineering layer to derive different style. And then it has the very unique possibility that is really, really interesting, I believe, to generate vector graphics also, and not only raster graphics, clearly from text prompts. Then we have the AI image vectorizers, which also is able to convert any raster image into vectors. And finally, the AI quote generator, in which we are using different LLMs in which we then parse structure output. All right, so on the basis of this background context, let's discuss now how the AI landscape has changed and where we come from. Before we dive deep, I want to reiterate, as I mentioned before, that for the sake of time and complexity, this is a simplification, a slight speculation, and cannot possibly cover all the different approaches that companies have adopted over time. But that's what I've seen for the majority of my experience, at least. So the background context we have seen aims really to put things into perspective, right? We've built all these AI services that you have seen in less than a year in 2023. Now, if you take a moment and you think about it, how much time would it have taken only 5 years ago? It is close in time, but at the same time, it feels like an age has passed. And in the AI time, most likely it did. So 5 years ago, not considering that architecture like latent diffusion models were in the first place not as explored as they are today, same as, for example, large language models, the AI or machine learning process was on a high level as following. There was the need for large-scale data collection, which then called the need for large-scale data cleaning. Then one would have needed to basically select neural network architecture. Then there would be the need for in-house training, compute provisioning. Then there would be the need for training, performance evaluation in its simplest form, qualitative and quantitative evaluation. Then this would have been repeated, right, until defined metrics were satisfied, until stakeholders were satisfied. Then we would need to go into serving. So basically optimization for serving. And in this case, we would need to do most of the time self-managed model deployment, right? So either create a custom cluster whenever we needed auto-scaling using on-prem machine or using virtual private servers. And then we would also need to kind of implement most of ad hoc monitoring solution. So this was a very large, complicated, and prone to error process that was still to create relatively small models that were very specialized on a specific task, not really steerable once trained, and it would take months to go end to end. And there would be the need still for a full team of engineering needed. We would need data engineer, data scientist, machine learning engineer, and so on and so forth. So that was around about 5 years ago. Again, a little bit of a simplification just to pinpoint this in time, just to see really a comparison. Now, if we move the clock to 3 years ago, we can see that the ecosystem was not really mature, right, with respect to infrastructure. If we go again 3 years later, now cloud providers started to offer managed services, for example, SageMaker in AWS, to simplify training and inference using on-demand compute resources that could scale in and scale out. So again, seeing the same kind of points, the large scale data collection remained. Then data cleaning started to be taken over from cloud computing that now started to offer services to easily improve, clean, and label dataset. The neural network architecture selection remain, training infrastructure provisioning now, and this is very interesting, moved to cloud computing, which again could offer scale in and scale out and on-demand resources, so there was no need anymore for in-house resources. The training and the performance evaluation loop remain, and also hosting started to shift as well to managed services, right? Where you would still have to write the scoring script, say, but the underlying deployment cluster or machines would be managed by the cloud provider. Finally, also monitoring started to shift to managed services and simplifying model quality checks and distribution drift once deployed. So the models developed in-house remain small, specialized, but going end-to-end now was quicker and more effective, given that these managed platforms were helping a lot with the infrastructure around it. At the same time, there were other open source alternatives clearly that started to pop up, right? So it's not only cloud providers and closed source solution. For example, MLflow, a very popular one, is one, but that still requires self-hosting. So it's always a little bit different in terms of how easy it is and how immediate is the jumpstart for developers. Also, the first foundation models are starting to kind of appear and really get traction, like for example, GPT-3 in 2020. And this is starting to bring a fundamental change, right? So for the first time, we start to have huge models that don't need fine-tuning or additional training at all, and can be simply steered using few examples or none at all, actually, when we go to zero-shot learning, right? So the potential here, it's really huge. Again, then we move the clock to 1.5 years ago, and things have already significantly changed a lot. So from large-scale data collection, we pass now to small-scale data collection, and same for data cleaning. So now, basically, we don't need really this large data set anymore, like to create new models from scratch for a lot of use cases. So also, while more architecture clearly exists and still are used, the majority of applications are shifting to transformer. It clearly started with NLP. We, I guess, are all very familiar with that. And then took over also for computer vision with visual transformer. And then we start to see basically the rise of diffusion model and architecture. They were already introduced, right, in the literature in around 2015. But at this point in time is the timeline when they really started to be adopted and greatly improved. Training compute was provisioned using managed services, which now support different GPUs, and the developer experience just greatly improved. I think everybody that has been in the field for enough time has the experience of that, how easier and much more developer friendly and mature the thing has become. So training, as I mentioned now, becomes mostly fine-tuning. So we can take an existing model and with little data and training only adapt it to a more specific use cases, which then also helps in terms of time, in resources, in terms of the team needed as well. Model optimization can also be done now using managed services and frameworks like ONS, and monitoring, as before, can be done using managed services, which are now effectively covering every aspect of the ML or AI lifecycle in a very, very effective way. So this started the trend of having larger models instead of small ones, fine-tuned on specific use cases and served using cloud services, or that was mostly for OpenAI, right? But also in the case of foundation models with APIs that were basically completely and fully managed. So where we had no control over the infrastructure and we were only using the service and getting value out of it. So now this brings us to today. if so much has happened in only 5 years, this brings the natural question, where are we today, right? So continuing on the same point as before, for a proper comparison, we moved for training from large-scale data collection to small-scale data collection, or to even just few example data collection that is specifically for few-shot learning, which we're going to speak a little bit more later. But this can also be brought to an extent where there's no need for example or data points at all in the case of zero-shot inference. As a consequence, for data cleaning, we have moved to have small-scale data cleaning to no data cleaning at all, and that happens specifically for few-shot or zero-shot inference. And as before, we have seen that architecture are mostly in transformer and diffusion models. Also, training compute provision changed significantly, with cloud managed services being extremely mature in providing end-to-end support for all the AI lifecycle. But at the same time, and I think this is where it started to become really interesting, specifically this year, we see serverless fully managed service appearing. First, we have seen this already with company like OpenAI, right? You're one API call away from a large language model, from a huge foundation model. But now this trend has been also adopted by the big cloud provider. So we have AWS Bedrock, for example. We have foundation model catalog in Azure. So in a sense, we are really starting to see a shift there in, again, letting the infrastructure to become more and more abstract and really focusing more on the value we can extract from the model. Then continuing on the point briefly, for inference and monitoring, in the same way as it was with training, we're transitioning from self-hosted model to foundation one in a serverless way. Then again, depends a lot on use cases. It still make a lot of sense to self-host models, specifically open source one, also for large language models. But again, this rise of serverless in infrastructure, serverless inference for huge model, it's something that I want to stress on, that I think it's a very, very interesting trend. So if 5 years ago one needed to self-provision a cluster, and 2 years ago one didn't need to do that anymore thanks to cloud provider, today there's the possibility to not even think about it thanks to fully managed services. So this again enables developers to just focus much more on the value you can extract from models rather than the technicalities and the infrastructure around it. It's a huge shift, and it's, I believe, the main reason why we see AI integration happening almost in every sector and part of life, regardless of company, regardless of team sizes. Now you're literally able to get this huge value from models that before was locked in either in big corporation or like very complex team, and now it's basically available to everybody. And I think that's quite exciting. So now I also want to go briefly on these a little bit, right? What has changed with foundation model, specifically applied to LLM, but this also applies to computer vision models. So as we said before, we need to have specialized model for specialized tasks. And today, thanks to foundation models, specifically with NLP, with LLMs, we can natively steer them after large-scale pre-training and alignment with reinforcement learning from human feedback. One way to do this is with zero-shot learning, in which we simply create a question or command in natural language, and then the model will do the best to oblige, and actually very well in majority of the cases. For example, we can, I guess everybody has played with ChatGPT, and you can just give zero-shot prompts, and then it's very likely actually to get already good results from there. But then, like humans, context helps a lot. By giving more context, providing examples, LLMs are able to understand better the user intention and act accordingly. They have an impressive ability to adapt to different styles, situation, and task. And that's really what makes LLM and general foundation models so powerful, that they start to become general real models, and they can really adapt to different situations. We can, for example, modify the example before to generate in the same poem we had, but now following a specific style. And giving only this really small example, we're able to steer the LLM towards the style that we really want. And again, this is pretty amazing. And if you think about it, it's truly a radical shift in the way traditional ML was done. You need to have a whole new model to have a different style, where here you can, at inference time, add just a little bit of prompting and get immediate value out of it. And again, that's a huge, huge, huge shift that even 5 years ago would have been almost unimaginable. Then finally, there is a retrieval augmented generation. So as we have seen, context is good. Generally, the more context, the better, right, as humans. But what if we have too much text, right? What if there is simply too much context? We know that one of the issues of LLMs, it's context length, and the fact that we cannot possibly fit an infinite length text because of memory issue. For this, retrieval augmented generation comes into place, only giving the LLM the relevant information to shape its context at inference time. But then the question becomes, how can we find what is relevant information at inference time? The most common approach is currently made through embeddings, where we take string, we project them in a higher dimensional latent space, in which tokens that are semantically close are physically close in this space, and we calculate these distances. So for example, golden dog, golden retriever, husky are all closer together than, for example, dog and fog that are far apart, even though in pure lettering, one could see that dog and fog are actually close, whereas semantically, they're clearly very far. And by the way, this works in any modality. There's a lot of research in this sense for multimodal models where embedding are extracted for images, text, video, audio, even sensor data, going really towards multimodal LLMs and multimodal AI in general. In practice, how does retrieval augmented generation work? The process is following. We take a large input text, for example, a whole code base documentation or anything that is quite large. We slice it up into slices, compute the embedding vector for each of them, store them in a vector database, common, for example, pinecone or quadrant. And then at inference time, we compute the embedding of the vector input. We find slices that are semantically close in the database, and we add these to the context of the LLM. So in this way, we are able to get the relevant information at inference time that we can put in the context of our LLM. All right, so with that said, let's recap a little bit this section. Where are we today? We have seen that the AI landscape has changed dramatically. Foundation models have created a whole new approach to artificial intelligence, in which we have now one big model capable of generalizing, easily steerable, instead of many different models. Also, serving model has really shifted. So from self-hosting open source model or creating architecture in houses, now we are able to use just API calls in a serverless fashion. So basically forget completely about the infrastructure behind it. And then this also then spiraled in that the pace of development has completely changed. Now it can take days to create a proof of concept with zero or few shot learning, and roughly the same amount of time to go to production. And for example, for some application, this would have taken months and full teams only, again, 5 years ago. And also very interestingly, now we see the rise of companies that have heavily invested on models that are really rivaling with actually big techs, and that's actually pretty interesting to see. OpenAI, it's a clear example, right? One could argue that now they are quite big, but for example, things like Stability AI, Cohere, all these new companies, it's really interesting how the balance it's shifting in this sense. And finally, this brings us to tomorrow. Where are we going? So from small specialized models with specialized architecture, we move to huge foundation models that are able to generalize and perform zero-shot inference with the possibility to fine-tune and on small and specialized tasks. The Chinchilla law, which is linked there, shows that the majority of the model are still undertrained with respect to their parameter number. So there is still much room to grow by using bigger and higher quality dataset or by finding a balance between parameter and dataset. So as I mentioned, from moment of development to deploy a model, we can do that in a week. There is also an incredible development in optimizing inference, for example, with quantization, LoRa's, parameter efficient fine-tuning. We even have LLMs running on iPhones. And then there is very interesting research actually in going completely opposite in a sense of what I've mentioned up until now. So going again to smaller models, relatively smaller. So basically having smaller models with higher quality data set that are ideally able to perform as good as the bigger models. And finally, some concluding thoughts. So I think we all know that AI winter is finally over. So there is simply too much value in AI for it not being used. It is pervasive. It will become even more pervasive. The next wave is coming with multimodal AI. So we have already some example, again, in the consumer space, with GPT-4 vision, right? But also there is a lot of happening in the open source space. And clearly this is the next step, and that's gonna enable even more value from those models. It's possible to get started today with AI, extract incredible value from models served through API, no need to think about infrastructure serving any of those things. And this enables a wide variety of use cases that was simply not possible before, not even thinkable before. Or if it was, that would have been needed months and large, very specialized teams. So now really this is democratized to almost everybody, and that's pretty exciting. So again, if you haven't started already, start experimenting with them and think more about the value you can extract from them or you can create with them rather than the complex technicalities around it. Because today we are really one API call away from value. All right, that was it. Thanks a lot and happy to answer some questions if there is any. I'm not sure if there is because I haven't seen.
Yep, you've got one in the Q&A widget. You did have a couple of questions in the webinar chat, but I went ahead and answered those for you. So if you want to tackle the one that's there in the Q&A, that'd be awesome.
Yeah, good stuff. Pietro, what do you think of image embedding, especially with the granitary similar image? My other question, why smaller model doesn't mean that the quality of the data is that. Yeah, exactly. So image embeddings are also extremely exciting, right? And we have seen that they already work really well, for example, with Clip and these kind of models. And we can only expect them to be more and more integrated with more models, again, as we go to multimodal AI, which is extremely fascinating. And again, extremely exciting. Where can we, okay, then that's possibly another question, not for me. Why smaller models? Smaller models, exactly. Like we have seen that data is generally always what drives good models, has always been since the very beginning of machine learning to today. So what Microsoft specifically is really trying is to create really high quality data set with small models. And then by having those really high quality data set, there is already some evidence in the literature that they can perform as good as bigger model, which is again super exciting. The landscape is clearly really rapidly changing, right? So we need to see where eventually we steer. But in general, there is also a trend there that for things that before we were using huge models, now we can do them with smaller models. And I think this is a continuous loop. right? So for example, now a Llama model is performing better than a GPT-3 model, even though it's, I don't know, like half its size, right? So there is also this trend to consider. Hope this answered the question.